Okay. Ooh, wait a second. Okay, well, I think this works actually. Sorry. iPad, rough. Go, go, go. Let's lock this. All right, we are going to be introducing deep foundations. So please review all that stuff from shallow foundations, bearing capacity, and all that fun things, especially the CPTs and SPT procedures from the lectures where I was gone. Next 4 lectures will be talking about piles, pile designs, and just kind of skimming the surface. There's a lot of just options for piles, and that's why the project reports are kind of supposed to supplement towards that. But we'll cover at least just generalized tip resistance and bearing capacity of piles, as well as looking into drilled shafts, but can't cover everything. All right, just wanted to touch base with the projects here. We're in week 12, not week 11. There's only one group that I don't think I've gotten the information from. So unless it was an email and I didn't see it, but yeah, if you guys just choose one, these are the ones so far. Let me know if those look like something that you're not planning on presenting on. These are going to be due December 7th here. And then just a heads up too, you do have homework 3 that's going to be due this Sunday? Friday? That's Friday. Okay, yeah. Do we have class Friday?
No, it's Veterans Day.
Yeah, it's Veterans Day, right? Okay. How's homework 3 going? You guys been able to like look at it?
This week, Dylan, I'm not starting until Thursday.
Okay.
Rated this week.
I might extend it, but you'll probably have some overlap because we have a homework on piles too. So I'll probably extend it to Sunday at least, just so you can have that time with the holiday and stuff. So yeah, I'll probably end up just doing that. The other thing I wanted to talk about, I haven't posted this yet. Right now, you'll see on your schedule, there's no exam 2. I was planning on having the exam 2, like obviously there's going to be an exam 2, but I was planning on having it after November or after Thanksgiving. I'm going to post a poll that's anonymous on Canvas. Just want to get your guys' input. The way class is going, we can actually finish these deep foundation lectures a little bit earlier. And then I'll probably just do an exam 2 review lecture, video lecture that you can watch on your own time. And we could have the exam 2 due before Thanksgiving break. So I'm going to post a poll on there. Right now it's scheduled. We're going to do it after Thanksgiving break. If you'd rather prefer that, then just, that's fine. Like answer the poll saying that you'd rather prefer that. But if it's 50-50 split, then we're just going to keep it after Thanksgiving. But I at least wanted to get y'all's input. With Thanksgiving travels and other exams time and everything, since this exam does usually, take a couple days, right? Since it's a take-home exam. So yeah, be on the lookout for that. I'll post that on Canvas and I'll write an announcement too for everybody who's not in class. Okay, so we're going to introduce deep foundations. Today is going to be a little bit more conceptual. We'll talk about the different types of foundation solutions for piles, and then the different theories that are based on that. And then we'll get into the fun old equations similarly to the bearing capacity equations as before. Just to recap some of the things again, for shallow foundations, the capacity or the strength that we talk about, this is going to be the bearing capacity. And the way we show this is QU. So although we have input factors based off of the shape of the foundation and the depth of the foundation, this lowercase qu is technically a soil strength value. Like this is the capacity of the soil, the bearing capacity of the soil. What are the 2 methods that we talked about for bearing capacity? Terzaghi. What's the other one? It's not a guy, it's a super long acronym. Yeah, AASHTO method. Those are the 2 like standard theories. And the reason I'm choosing these 2, because there's more out there, is that these are the ones that are provided in your FE handbook and your PE handbook. So for whatever reason, they use these two. Does anyone remember the difference between the two, or what's the main thing that AASHTO adds? Yeah, shape factors. Yeah, there's these little S's. So it's like S gamma, SQ, and then SC. So both techniques still look at bearing capacity in terms of three factors: the cohesion, the unit weight, and then the surcharge. So there's those three separate factors. Each one of them has an N, like a bearing capacity factor. These are called bearing capacity factors. And the tricky thing is there's Terzaghi bearing capacity factors and there's AASHTO bearing capacity factors. And both of them still use this. They use the same variable. So N subscript C, there's a table with N subscript C's for Terzaghi. And there's a table for AASHTO, same variable. So make sure you're choosing the right one there. So we kind of went over an example last class about this. There's two kind of ways that you can look at using bearing capacity. You can find the bearing capacity of the soil and then check it against the applied bearing pressure from the foundation. Or you could find the bearing pressure from the foundation and then design the value based off of a required like loading. So like knowing that we have a structure load applied, or a structure load that's often fixed, such as capital Q, which is a force. Usually by the time the geotechnical engineer is working on creating this foundation, the superstructure is already pretty much set. The structural engineer knows that the column is going to apply a 100 kip load or something. So then it'll be your job to design the actual footing size. So that the actual like footprint of it. So there's different types of sizes of footings, you know, like this little footprints and everything. And again, what we're trying to look for is the soil strength, which would be the Q ultimate, to be greater than the applied stress or the bearing stress. So that would be Q divided by A. So we would find the bearing capacity based off of an assumed factor, based off of the assumed shape, you know, length, width, or depth, or base, or something. And then we would check that, and then with our applied stress, with that cross-sectional area, we will see if that value actually works. And then we would have to redesign it if it doesn't. Now, eventually, though, you'll see that there's a point where there's not enough footprint available, since we're changing, or not enough area available. So you would be calculating the bearing capacity factor, or sorry, not the factor, the bearing capacity of the soil, and you'd know the Q load, and then that required A cross-sectional area. You could say like, okay, our site is not large enough to have this footing. And in that case, we would need to use a deep foundation. Can anyone else think of another reason why we might need to use deep foundation over a shallow foundation?
The type of soil you have on the very top couple layers.
Yeah.
You might need to drive it down so you have stronger soil to support the structure.
Yep. Yeah. So another, like, technically that would be like if punching shear was occurring. So punching shear prevalent. Yeah, so if you have a weak soil on top, or low density soil, or something undesirable soil organics, then you would need to push that to a deeper level. So for that, we use piles, drilled shafts, caissons. These are all types of deep foundations. Essentially, with a deep foundation, a way of characterizing it is just anything that's not a shallow foundation. It's where the depth or the length of the whatever it is greater than, much greater than the width. Another way of thinking of this is that instead of transmitting the stress horizontally across the soil, we're transmitting it vertically now. So footprint before, or that area is a cross-sectional area of a horizon or a plane around the surface. But for a pile foundation, then we transfer it vertically through friction and then a little bit by end-bearing loads. So most of the time, a shallow foundation is going to be the preferred way of doing just typical structures. And then deep foundations are just going to require more work, a little bit more testing and uncertainty. So they're mainly only used for like high important projects or when soil is really poor. So the following are also some recommendations for pile foundations. Not only can the soil be weak, like this one here, so this would be in weak soil conditions where we need to transfer the loading to a stronger stratum, so like a rock down here. But also for carrying lateral loads. If you think about it, if we're assuming the connections are all rigid, a deep foundation will lower the center of gravity of the entire structure by extending it below ground. So it'll be able to withstand lateral loads a little bit better, not have a high overturning moment. Another one is if we have expansive or collapsible soils. So in some areas in the US, like Texas, Louisiana, they have a clay that can swell whenever it becomes wet. So in flooding seasons, it'll actually push up structures. So in that time, they might push the deep foundation to a more stable soil. So essentially the soil above it can rise and fall without putting stresses on the superstructure itself and causing tilting or anything. Another reason might be to resist uplift. So this is actually for like tension piles, which I saw a group wanting to do helical piles. This is one of the applications of helical piles. It's essentially like a screw that's taking resisting uplift in case there's overturning or for, think of like the tension wires on those big telephone poles, or not telephone poles, what are those things? Cell lines and stuff, like the one right by Jag Stadium. And then the other one would be for areas of potential erosion. So a lot of times you'll see bridges that look like they're on shallow foundations. You'll see a big cap here, but then there'll actually be piles underneath that. And that's because if river ends up eroding away that soil and flash floods or anything, we want it to have sufficient amount of strength to hold up that bridge and not just have extensive settling. So we're going to talk a little bit about the different types of piles. Some of these are some pictures. This is actually from, I think this is I4 Ultimate. So not only can piles be used to withstand loading or like for structural loading, but they can also be used as a construction aspect. And one of those would be like soldier pile walls. And this is an example of those soldier pile walls here. These are used for retaining walls. And essentially what you have are all of these H piles or W members. Usually they're H piles. And then as you are filling in soil, like, so this area right here would be probably filled in with soil. You would install, it's essentially just like 2x8s or 2x12s, like boards right here. Has anyone seen these on the side of the road before during construction? So these walls these piles are penetrated in the ground, pushed in there, and then they fill up and essentially fill the gap here so they can fill up with soil on the other side of it. And so these would be called soldier pile walls. I don't know why they called them that, but it's kind of a cool name. And that's really helpful because these are also temporary often as well. These H piles, since they're spaced pretty well together, they can be vibrated in and then vibrated out. So you can install these and then just stack the wood, fill it up behind it. And then whenever you're done with that temporary retaining structure, or if you're switching the road around, then you can take the wood down and then vibrate the piles out, since they're not as deep as some of the other conventional piles. Some of the other examples, H piles can also be used in grouping. What we'll see with H pile, these are beneficial because they are usually vibrated in. Since they are friction piles only, they don't have a lot of end bearing resistance. So you can see that H kind of maximizes the surface area of the steel on the metal. And if you shake these at a high frequency, it essentially just liquefies the soil so you can move it into the ground. And as soon as you stop shaking it or vibrating it, the soil locks back into it. So these are very common in organic soils or some type of like more loose material. And if you combine a bunch of them together, you essentially make like a mass of stiffened soil that acts as a deep foundation through the whole way. Timber piles are some of them. Timber piles are environmentally friendly, even though we're using the environment to destroy the environment to use them. But it's better than having still lower of a carbon footprint than producing steel or concrete. And then concrete piles. So this one looks like it's an octagon pile. I've personally never seen concrete octagon piles. Most of them here are going to be 24-inch concrete piles. And then also steel pipe piles as well. So these are just some of them that you'll see used a lot. For typical roadway construction, you would use steel pipe piles in organic soil or clay soils, and then concrete precast piles in like sandy soil. That's like for like DOT stuff.
What's up with the creosote piles? Are they not using them anymore?
What's that?
The timber piles, they're soaking the creosote to help with erosion and all that.
Oh.
They stopped using it, but I don't know what they're putting on them.
I don't know about that. The only thing I know about those is some old projects, like if you're tearing up like a site, they'll come across those piles. Yeah, I don't know exactly what they would use those for. Maybe they still use them for like jetties or other like high organic areas. But a lot of these wood piles now too are like composite piles, like composite wood, or where they have like something over it. Like the new walkway that went from whatever the side of campus to like that police station area. I think those are all those new composite like piles that they just drive in. Yeah, I know they used to like just pour diesel fuel on them too, right? Or something. Yeah, I was like, that doesn't sound good. But yeah, most of the time, DOT and heavy stuff, you'll use concrete or steel. But yeah. Let me see if this will actually work. I don't think it will because I'm on an iPad. Okay, well, it's kind of an old video too because it's made by FDOT. But if you want to look back in the notes or yeah, never mind. It's not worth trying to find. This is a video that kind of talks about the pile driving for the I-4 Ultimate project, which is pretty interesting. Most of these pictures are taken from there. This one too. They had some of the, like they beat the world record pile driving length with spliced piles. And with the I-4 project and their new project too, that's the Wekiva Parkway project. If you want, you can just Google Wekiva Parkway. Actually, in a couple classes, I'll show some geotech reports for this. In this area, there was so many potential sinkhole problems with this, where the road was going, that one pile like would cap out, like hit limestone at like probably like 100 feet. And then they'd move over like 10 or 15 feet and the other pile would cap out at like 300 feet. So the longest or the the tallest or the deepest single pile in the state of Florida is in Orlando for I-4 Ultimate. I think it was like 440 feet in depth, because once they start driving the pile, then they're like, all right, well, we're just going to keep splicing it and keep adding on to it until we reach that resistance value that is designed for. So yeah, it can get really expensive really quickly material wise, because you could design for one thing, but then once you start actually constructing, then you have to wait until you reach that actual driving force. Well, different types of piles. Timber piles, these are, again, just kind of a standard for concrete, steel, and composite. We'll be focusing mainly on concrete and steel, but timber piles you can still come across. Composite piles are now starting to be more popular too, for high strength. But really the material plays a role with the friction, but like essentially the goal is the same thing. It's to transfer the load from the structure through friction and end bearing instead of or horizontally. So for construction methods, there's different types. There's cast in place. This is usually what we'll refer to as drilled shafts, but depending on who you talk to, some people say it's like a size requirement, but essentially for cast in place, you drill a really, really deep hole, you lower, or you put some method of retaining the soil, like either mud or like some type of casing, and then you lower the steel reinforcing rebar into the hole, and then you fill it with concrete. So that's casting in place. You're literally casting the pile in place. The most common kind is going to be precast. That's the opposite. You're casting the pile beforehand in the yard, at the gate, precast lab, or whatever, the construction site. And then you're bringing the piles on massive construction or massive semis, and you're installing the piles at the site.
Is there a depth where you kind of like switch over from one to the other?
Not, yeah, precasts are better for high, like deeper depths. It's going to be like more so loading potential and the soil type too. Cast in place is usually really good for end bearing because they're larger. And usually the friction is hard to actually design against because you have some type of system to keep the sides of the hole open. For precast piles, you can do designs and you can make sure that the friction of the concrete or the steel is sufficient. So when you're driving it, you're essentially testing the loading as you're driving it, you know, like to push it in. So precasts are usually for deeper. Or it's like a loading or a soil scenario. It's
So
not.
you got it, like you said, in the Chicago, a 300 foot, you know, drill down. Or you have 300 foot, it's not going to be a 300 foot beam. So would they just cast multiple? Would they have multiple beams and then they tie them together?
Yep.
No.
Yeah, with that's one of the main differences too between concrete and steel. Steel, they just literally weld it. And they do that. For the concrete piles, you can splice them still. So they're precast piles, but then they'll literally, as they're driving them, they'll drill into it, install rebar, put like another mold, and then splice another pile on top of it. But that you can only do so many times because, you know, it's a point of weakness, like where it could buckle. For steel, you can keep welding that thing and just keep adding on as it goes down. Yeah, some of the shapes I've already kind of mentioned, but circular cross section, or what we would call these, are pipe piles. And they could be hollow or they could be capped. The H piles or I beams. So if you look at your steel manual, if you guys have had that yet, these are not W piles, they're H piles. So they're more so like an actual H and not a wide flange. So for H piles, the flange and thickness and the web thickness are the same. They're not like the I beams, not structural I beams. And then other types are like squares. And sometimes you'll see octagons and that kind of thing. And then there's two main installation types. we have what's called displacement. And that is when we are driving the soil or driving the pile. And so displacement, that means we're displacing soil as we're driving the pile in. And the installation type is going to greatly affect how the pile responds to loading. If you think about it, like if you've ever like just tried to push like a rod into the ground or something, like even just like a shovel or something, or a piece of rebar, like you'll notice that as you're pushing it in, there comes a spot where you can't push as hard as, like you aren't able to push it in. So that in itself is almost a way of checking the capacity of the pile, the driving resistance. The other type would be just what we call replacement, which means where we are removing soil and then putting a pile there. So this would be like cast in place, but you could also do this for precast piles. This we use augering. So I mentioned one of the topics you can choose is an auger cast pile. That's kind of like a combination of both, where they use an auger, which is like a drill bit that will drill down into the soil. And then as they pull up, they fill it with concrete. They actually shoot concrete out of the tip of the auger. So they drill down, pull it up, and then as it's pulling up, it's shooting concrete out and filling the hole up. So it's casting in place while it's augering. So these are for different types of techniques, and we'll talk about those later too. All right, so for steel piles, here, well, let me finish this out here at the bottom. I already mentioned this, but the goal is to transfer the structural load through what we call skin friction, which is a weird way of saying it, but that's the actual term that engineers use, and a little bit of end bearing. So when we start doing calculations here, you'll see most of the time the capacity of the pile is going to be taken from the skin friction. So actually the vertical interface with, like if this is the pile, the actual friction along the outside of the pile with the soil. Most of the capacity is going to be that. But there's also some capacity here at the end as well. Okay, so for steel piles, these are usually, most of the time for structural components, are going to be pipe piles or rolled steel H piles. So you can see those are H piles. These can be whatever size you need them to be. Usually this is where like drilled shafts are also going to come in, or suction casings are going to be these as well, like these larger diameter and larger thickness steel piles. Typically for pipe piles like this, we'll use 24-inch pipe piles, which means the outer diameter is 24 inches or 2 feet in diameter. That's like the standard for FDOT. And the good thing with these is they can be both driven or vibrated in. So I mentioned before H sections, that's like the structural section here, these H piles. This is preferred over other types of like W sections or I sections. And the main reason is because the web thickness is equal to the flange thickness. So if we remember from I don't know when you guys would have learned this. I guess mechanics of materials, or if you took steel design or something. So if we have something like this is what we would usually call like a W member or like a wide flange. And you have your steel manual that has all the different section properties. This is going to be the flange. So there's two flanges at the top and the bottom, and then the web in the middle. And for an H section, that flange thickness is the same as the web thickness. So it doesn't make it the most structurally efficient for bending in a beam, but when you're talking about driving or vibrating a pile in, and then just when we're talking about this, the surface area of that, then that makes it pretty efficient there. So there can be other types like sheet pile walls here. These shapes, these are rolled steel shapes as well. So you could have those. But these aren't usually not load bearing. These are just for retaining walls or creating some impermeable surface or impermeable like sheet underneath a flow net, right? All this fun time. The benefit of the construction method is these can be extended through welding, so it's easier to extend. And often too, especially for hollow piles, these can also be filled with concrete. After, I cannot spell. After they've been driven. That's essentially what a composite pile is. So especially for uplift, tension uplift, if you're worried about like uplift capacity of these relatively thinner piles, you know, like pipe piles where they're relatively thin compared to other like denser piles, you could fill them with concrete, and that lowers the center of gravity or the weight of the whole structure. So we're not worried about uplift potential. So for steel piles, the application, most of the time these will be for fine grained or organic soil. Now it doesn't need to be, but thing to think about, like if you had a steel pile, or just think you had like a sheet of steel and a thing of concrete, which one would be more smoother? The steel would be more smooth, right? There's less friction on steel than there is of concrete. And the friction is the thing that we want to be holding a lot of the weight. So fine grained soil is going to be less frictional. It's going to be more cohesive. So the cohesion will actually help bond to the smooth surface of the steel, where for concrete, you would want a frictional surface on a frictional soil. So frictional surface on a granule soil like sand or gravel. So that's kind of like the rule of thumb when we're talking about piles. For fine grained or organic soils, think of smaller particle sizes that are more governed by cohesion. Then we would want to use a steel pile. So the pile has a smooth surface that essentially sticks to clays or silts. That's because of the cohesion within that. Oops. So the typical length can be anywhere 15 to like 60 meters. It's like 50 to 200 feet. But when I was working on like I4 Ultimate with with Terracon. There were some that we were designing up to like 350 feet. And that's designed. So we would actually, like, we knew like Ivanhoe. We knew they were going to be at least that long. There's been some that are 400 feet, as you can splice them. Really, really deep piles, especially in Orlando or Tampa, where you have these old lakes that have been around and just decades and centuries of organic soil getting piled and piled up inside these lakes. You have to go through all that organic soil to reach the limestone. Typical loads, just these are kind of whatever, like it's super dependent on the depth in the soil. Yeah, 300 to 120 kilonewtons, but it's going to be dependent on the driving technique in the soil as well and the size. Typically, vibrated piles are going to be less capacity because you're not actually you're not able to penetrate into the depth or the soil as much as a driven consideration. Things that we have to think about for steel piles, or can anyone think of like some potential issues using steel piles?
Salt, alkalinity of the soil.
Yeah, huge, right? Corrosion, everything. Which also makes it tricky because pipe piles and steel piles are really helpful in organic soil. Organic soil is going to be slightly acidic, so you have to treat and ensure that you're using the correct type of pile, or you're pushing it past the organic soil, so you don't have future corrosion issues. So usually anything with a pH less than 7. Need to consider coating or some type of additive to the or some type of coating or additive to the surface of the pile, so you don't have future corrosion, because we're designing these things to last for a long time. That coating can affect the friction. So we'll see when we start looking into the design of the friction of the pile, you'll see like different types of coating that might reduce it. Anything else, especially for like driven piles, like these piles that are hammered into the ground? Yeah, deflection or deformation. They're not rigid, especially some of these thin little pipe piles. So deflection during installation. Because what's happening underground, you usually can't even see, right? Like, so you're driving this pile and all you see is the pile going down and you're like, it should be hitting some bearing or rock layer at this depth, but really the pile is moving sideways or deflected and you can't really tell. And that's actually a case. You can get like buckled ends of the pipe piles there while it's actually being driven. So you need to ensure that the actual hammer that's driving the pile in is not hitting it too hard, that you're buckling the pipe up there, or that it's pushing through if it hits like any type of underground utility or something, that you're not breaking the pile that way. So the issue with this is it's unknown to the contractor, right? Because all they see is the pile going in the ground. So like one of the examples, this Lake Ivanhoe that I already talked about, where we had all these deep piles. This bridge is finished now, right by north of downtown Orlando. But we lost like, I think a couple 200 feet pipe piles, which means they were driving them into the ground and then it wasn't hitting the rock that they thought it was, and it was bending over and they couldn't actually like keep driving them. So they just pushed it in the ground and then moved it over and installed a new one. So there's these massive bent pipes that are underground forever, essentially, you know. So that happens a lot in Florida, actually. We'll let the future people, the aliens, worry about that or something. There's another example. I couldn't find the picture of it, but I remember in my class they were showing this too. It was an H pile that they were driving into the ground, and it was bending at the perfect radius where it actually never buckled, and they kept driving it, and it poked up through the house, like down the street, because it was just driving and it was that perfect radius. So you always have to consider that. You want the pile to be stiff enough that you're driving it, but not too stiff that it's too hard to drive. You can't vibrate it in. So that's the issue with steel pipe piles, or steel piles in general. Oh yeah, so that's one of the pictures. Actually, you can see the pile grouping there. These were all down to like, I think these were like 300 feet piles. When you're driving on the side of the road and you see these piles too, you'll see numbers as they're being installed. That's the length of the pile. So the contractor will do that when they're splicing them together. So if you're driving down and you see like 200 at the top of the pile, that's not the pile number, that's the depth of the pile, or the length of the pile underneath that. Always in feet. So the advantages. They're easy to handle and extend. So as far as transporting, they're massive pipes. And although they're hard for us to pick up, they're lighter relative to massive concrete structures. Like since there's lower density, less amount of material. They can be vibrated in. So that's really helpful instead of driving piles, which concrete piles can only be driven in. So steel piles will allow us to be able to just vibrate them in. As far as compared to timber piles, they can still penetrate hard layers. Like for the most part, steel's pretty strong as long as you are carefully driving them with not too much force. They have adaptable geometry. So some steel pipe piles can actually be tapered, where they're smaller at the bottom to help with that driving and then help activate the friction a little bit more. And still they can have a high load carrying capacity. So some of the disadvantages, they can be pretty costly because you're using a lot of steel. If you are driving them into the ground, then it's very loud. So the contractor, especially in residential areas or in business districts, they might have to consider that and not drive too early or too late, or they have to make up for like if you're next to like an assisted living or something, or some sensitive areas, you might not be able to drive piles into that because of the loud or the sound. Corrosion is a big issue too, disadvantage with these, but nowadays we can do different painting or different coating, but that can essentially cut down the friction. And then the driven deflection for like, if you hit a hard layer that's unexpected, an obstacle underground, or if the hammer energy is too high. So these are the disadvantages of steel piles. So still applicable, especially in high organic areas or in like a fine grained soil, silts and clays. Orlando, essentially, if you're driving over a lake, you're always going to use steel pipe piles. So concrete piles, as I said before, these are precast or cast in situ piles or cast in place piles. And these are usually called drilled shafts. The main thing with concrete piles is these must be driven. They cannot be vibrated in. They're all driven piles. So a lot of structural aspects have to go into designing these. They can either be cast and placed. This is where you lower the rebar and then you cast the concrete piles like this here. Or they could be what's called like post-tension or pre-tension. And these are to add capacity to the piles. Did anyone go to the gate precast field trip with Dr. Al-Safdi?
Tested.
Tested, yeah.
I've been there before though.
Okay. Do they do piles like this? Have you seen that pre-tension piles? I don't remember if they actually do piles or not, but most of them are going to be precast piles that will be pre-tensioned, like pre-tension strands. So to do this, you have to extend the depth. Then you have to do it through splicing, which is kind of a pain. Essentially, when you splice, you're creating a point of weakness, a point of discontinuity in the pile. It's not like steel where the weld just essentially makes it act as a consistent pile. Yeah.
Far down and the little concrete, right?
Mhm.
So the part not right, so just like reinforcing concrete.
Yep. Yeah. Yeah, they're all going to be reinforced concrete. You would never have just like a normal pile with only concrete. It's always going to be reinforced. Because yeah, you're essentially designing a beam, even though it is mostly going to be vertical, there can still be eccentric loading. So you have to make sure that you're not bending, like the pile can still withstand or still be exposed to some type of bending. So you have to include reinforcing. Most of these are going to be simpler geometry. And most of them are going to be square. But you could still have round or octagonal. I've never actually seen a reason why you would do that, but they make them because there's pictures of them. So, and you could still add like little caps or tips to them to help with the driving, like a little point to help it like drive into the ground as well. Okay, so the applications for these are going to be most of the time coarse grained soil. So sand or gravel. So the whole reason is it has pile has a rough surface. So it grips. Sand through friction. So like sandpaper on sandpaper, it has that frictional resistance. Or if you had sandpaper on clay, you would just kind of be shearing it. So the length is very similar, like 10 to 60 meters. So it's like 30 to 200 feet. Usually 30 would be like the minimum pile. You would never really design a pile less than 30 feet for these concrete piles, just because you would need to transport it and all that stuff. So for concrete, 30 is usually the minimum. And then, yeah, you could continue spicing them up similarly to the steel, but you still have limitations. For typical loads, the loading is larger than steel piles usually. The main reason is because you can drive these deeper into harder soil. So eventually, if you keep hitting the steel, it'll either buckle the steel or bend the steel. So, you know, the deeper, the more resistance you want, the deeper it needs to go, or the further it needs to go into a harder layer. So concrete, we just have the hammers set up so we can hit them harder and they can actually go deeper or into a harder layer so we can get a typical higher loading resistance. With that though, the considerations, there's still a couple of them. The main one is going to actually be the weight of the pile. With these, you have to be careful because if you add too much weight on a pile, over time, it can actually creep and settle. Because if you think about it, you're adding like, you know, in some cases, 100 feet of concrete, 100-foot concrete column. And although when you are installing it, you know, you usually install it till it doesn't go any further. That 100-foot tall column is really heavy and it could slowly settle and actually cause cracking or cause tilting of the structure, since it's a long-term dead load. So the weight of the pile needs to be considered. Transportation is also usually harder. The other one is driving requirements too. So you need to, they're usually harder to drive than a steel pile, which is good because that results in higher capacity, but you need to ensure that you're using more energy and the correct type of hammer to install those types of piles. So advantages, and this is just mainly compared to steel. So they're more economical. You can actually find the exact length or produce the exact length if this is a cast in place concrete pile. So if you know that there's a bearing layer 18 feet below your structure, your plane structure, then you just drill down to 18 feet and you pour concrete and there's your pile. And so you don't have to worry about cutting or welding, because oftentimes steel pipe piles or precast concrete piles just come in a standard length. They are more stronger and more resilient. So concrete is just more resilient, like long-term against corrosion and other aspects than steel and than timber. So they'll last a little bit longer. They're also much better in lateral capacity. That's why for concrete piles, what you can actually see is they can be battered. Has anyone heard the term battered piles before? You've probably all seen them. A lot of the bridges, I'm just going to draw like, this is our pile cap. You might have like some piles this way, vertical, like this. But then you could also have battered piles, which means they're installed at an angle. When they're installed at an angle, this helps, especially in Florida, against like wave action. So a lot of the bridges that go over bodies of waters will have these lateral or battered piles that help against lateral loading. Where pipe piles, you usually don't get as much because because they're just harder to install at an angle like that without them bending. So these are really good for lateral capacities. Some of the disadvantages, it can only be driven, so they can't be vibrated in. So in sensitive areas, you're going to be hearing a hammer hit the pile, all day. So inside cities, people don't like them. The transportation can be a pain. We'll show some pictures of these later on too. Some of these piles for the I-4 Ultimate, they had to like transport these piles within a certain time at night because they literally had to like cut down a whole highway or I-4, like the existing road, because they'll be like 2 semi-trailers back to back with an extension because they were so long. So, you know, the transportation, the logistics of getting a super long, heavy concrete pile from the precast yard to your project site needs to be considered. And then, yeah, the splicing to connect. So the connection points are weak. That's why usually we'll try to precast them to the required length. You know, they could be up to 60 feet, but then you have to worry about the transportation. So there's just all these other little things. Pipe piles can just be stacked on the bed of a truck, you know, and 30 feet increments and then just welded together as they're being installed. All right, and then just for fun, timber piles. These are the cheapest. So you would use these for like residential or city or docks or temporary structures. The design, I've personally never done anything with the design aspect of timber piles, but you might come across it still. So these can be driven or pushed in, which is kind of nice. So they can actually just be hydraulically pushed into the ground. There's these different classes of timber piles that you might come across. So Class A, Class B, Class C. I have seen them used for temporary construction work, where like you just need to like install something to improve the ground to get the cranes to come over, or the front loaders so it doesn't sink into the ground, like a temporary bridge deck over like a mucky area. And that's kind of what this is here. They'll install it and then like put rock or something just to stabilize the ground a little bit. And then most of the time they'll either drive these into the ground and just forget about them, or they'll pull them back up. Because yeah, if they're not treated, they're not going to last very long. So then for driving, it's obviously limited. You can't like drive it to a high capacity because the wood will shatter or broom. And so oftentimes they are also not extended. So these are the cheapest. They're also the shallowest type of piles as well. So shallowest deep piles, deep foundations. So yeah, shallow depths. So applications, mainly they're going to be like for boardwalks or like non-heavy loading. Some jetties, but usually not like lake or coastal jetties. And the interesting thing is these are actually favorable in aggressive soil conditions. The good thing about this is like, even though we think wood will rot and stuff, but that's because we a lot of times just use cheap wood that's imported in. But if you use local trees like cypress or other things that are actually growing in that area, and you make piles out of them, like especially cypress, then cypress is going to have a natural coating so it doesn't become rotten underwater. So you can actually use these in aggressive areas, because if the trees are growing in these aggressive areas like high organics or high sulfates, or even salt conditions, then usually the wood's going to be a little bit more resilient than steel. So you could use this in aggressive areas as long as you're keeping it local to the actual type of tree and type of wood. So some of these aggressive areas, this could be like saturated soil conditions. And like usually that's like salt, like saturated, like under like or swamps or something. And like other things like organic and marine. But again, they're heavily limited by the loading capacity. So you either have to have the spacing really close together like that, or you would use larger diameter ones that are just for like walkways, like wooden walkways or boardwalks. So for advantages though, they are the most economical as far as like production of piles. So they're the cheapest. And also they can actually last the longest in the right conditions. So you have to choose the wood wisely and also like use the right pre-treating procedures, but wood will last pretty long. Disadvantages: low loading, shallow, and of course, if you mess up the application of it or you use the wrong type of wood, then they can biodegrade if not designed right. So yeah, in this class, we're going to be focusing more on steel and concrete pile design. But what you'll see is the mechanism of understanding the ultimate pile capacity is the same for both. You just have adjustment factors. So just like how Terzaghi and the AASHTO procedure, it's kind of the same failure criteria. You just have different like factors. You have cohesion, whatever, and then you have these shape factors and depth of footing factor. The main difference between the pile type will be more so on the contractor side of things. As the engineer, you're going to use know what type is available based off the contractor, and then design the pile length around that. I think that was it. Okay, yeah. So we'll talk about the loading mechanism next class. I already kind of hinted at this, but it's a combination of what's called skin friction, so QS, and then point bearing capacity, QP. And since these are upper cases, these are all forces. So we kind of have to think oppositely here. We're not designing a stress like the bearing capacity is. We're designing forces. So these capacities will all be as a force, usually in kip or kilonewton. And yeah, this will probably be extended till Sunday. Canvas poll, just to see what the general thought is of the exam. And that's it. We'll get into actual numbers next class. So thanks, guys. Good to see you again. If there's any questions, also, I forgot to mention this on the exam. Now that you guys all saw the grades and notes and everything. Okay, cool. If you have any questions on grading format, like why I gave you the grade that you got, I'd be happy to talk through it and go through your submission. But
What are we gonna do after exam 2?
Like the Wednesday, right, the day before Thanksgiving, on the weekend.
it would be